Okay, we're talking about boosting. And just to recap last time, basically boosting, what we do is we say our h of x is a sum of capital T classifiers and in some sense what we are doing, we basically say each, so we assume each one of these classifiers is roughly, it's pretty weak, but it's better than a random coin toss, so at least it shows in the right direction. And then what gradient boosting does is we start out at 0, and this here is the n-dimensional space, where every dimension corresponds to a training point. And so this here is my y vector. And I would like to have my predictor point exactly to this y vector. The moment I do this, I have 0 training error. And so what I do is I have my first little classifier, and it doesn't predict y, predict something here, but I take this vector and take a step in that direction. And then I basically say, okay, well, I'm going to start here. Now my y's have changed, right? So one thing you can either, you update your y's, or you just say, I'm starting from here. And now you learn another classifier, and it points, let's say, gives me this as answer, right? Because they're pretty noisy. You take that vector and you take a small step in that direction, right? And you repeatedly take small steps into the direction of y. And because each one of these classifiers is a little more right than wrong, or points at least in the right direction, you have to get to y exactly, right? So that's the rationale, basically. And that's called gradient boosting. So you basically have a loss function. In every single iteration, you train a little classifier that really points you in the direction of the gradient of your loss function. Okay, any questions about this? One thing that's important is that there's 2 loss functions, actually, right? The first loss function is this loss function around y. We try to get closer here. And the second one, so if we are at a certain point, let's say we are here, and the gradient points in this direction toward y. And then the function that I'm actually calling my weak learner with says, give me a weak learner that points in the same direction as this gradient. Right? So the gradient comes from the global loss function I'm trying to minimize. And then every time I take a step, I call my weak learner by giving it a new target, and then it solves its own little loss function. And then gradient boosted trees, that's the square loss. Okay, any questions about gradient boosted trees or gradient boosting in general? All right, okay, today we are going to do the most famous boosting algorithm, which was also the original one. It's called Adaboost. Adaboost stands for adaptive boosting. And so Adaboost was actually what was originally invented, and people did not realize that what it was doing was actually gradient descent in function space. So the order is the other way around, right? So I just described it as gradient boosting actually is a whole family of algorithms. You can take any loss function and any weak learner. But that wasn't clear at the time. People just came up with Adaboost and just liked that algorithm a lot. And once they analyzed it, they realized that this was actually a very specific instance of gradient descent in function space. And so it took years for people to discover this more general framework, which is called gradient boosting now. And Adaboost is a very specific instance where we make a few choices. The first one is the loss function. The loss function in Adaboost is just the exponential loss. So it's e to the sum of all data points, e to the minus yi h of xi. Sorry, h of xi. That's the exponential loss. All right, so you remember this from your empirical risk minimization. So in gradient boosting, we kept that open. And the second thing is the step size. And here, we no longer set alpha to be a constant. Instead, we optimize alpha to take the ideal step. So optimize, so we call it actually a line search. What does that mean? That means we have this loss function, which is basically this exponential loss, around our optimal, the minimum that we try to get to. And let's say we are somewhere here, and we would like to take a gradient step. Before we said, okay, well, let's have the gradient points in this direction or something. It's a little noisy. It goes in this direction, right? So the gradient goes in this direction. The weak learner points in this direction. And we just said before, we just take a small step, some alpha, and we just fix it, right? Maybe 0.05. So we take a small step to here. In Adaboost, what we will do is we will say, actually, let's say I'm staying with this direction. Then I basically look at this whole line and say, what's the minimum of the loss? And that's right here. And I go all the way until my loss function is minimized. And that's my next step, right? So then I get a new weak learner. Ideally, I would like to go in this direction because the weak learner, let's say I go in this direction. And again, I take a step until my loss is minimized. Right? So that's the idea. So each step is basically of different length. But the good thing is when you finally find a good weak learner, and they're pretty noisy, right? But occasionally you will find really good ones. You take a really large step. And because of that, Adaboost can converge really, really quickly. And in fact, we will prove that it will always converge very, very quickly. Okay, so those are the two design choices. We have one more design choice, and that's what we are in classification. So it only works for classification. So the yi's are element of -1, +1. And we also assume that the weak learners only return us -1 and +1. So weak learners, they return h of xi is element of -1, +1 for all x. Right? So these are the assumptions of Adaboost. So first, so it's gradient boosting. We have to choose a loss function. So we pick the exponential loss. You have to pick how we set the step size. We say we will do a line search. And then we have to set the setting. In this case, we say it's a classification setting. And the weak learners will just be binary classifiers, +1 or -1. So it's a very specific setting of gradient boosting. And turns out when you do this, you get some very beautiful properties. And so as I said earlier, in history, it was discovered the other way around. So people basically first invented Adaboost, and then they said, well, could you also run this with a different loss function? Could you also run this with different settings here, and so on? And then that's how people noticed that actually this is a much more general, boosting is much more general than Adaboost. Okay, any questions before we dive into it? Okay, good. There's going to be a little bit of derivations today. There will be a demo at the end. So please bear with me. It's really not very complicated. Actually, this class is never really complicated. Just stay with me. There's like 3-4 steps, right? And then we get there. So the first thing is we have to go through the same steps as last time. And that was, imagine we already have a function h. We want to know what is the next weak learner that we should get. Okay, so let's for now just assume, don't worry about alpha yet. 1 second. Okay, yeah. So, when you remember so you basically want to have alpha plus alpha times little h, you want to find the next, you want to find the h that minimizes our loss, right? So you basically have, the loss function. Okay, so we did this last lecture or 2 lectures ago, right? So given that we already have a bunch of weak learners, which one should we add now, right? So that's basically the part of the boosting, but you call the weak learner and say, give me one more function. I'm not going through the derivation again. Basically what we have to do is we have to take the gradient of this function with respect to h, right? And so let's just do this. So that was previous lecture. 1 second, let me just make sure. Yeah, so let me define this. So the gradient of the loss function with respect to h of xi, one particular xi, is, if you look at the loss function, where is it? Up here. I give you a minute to maybe figure it out yourself. Up there is my loss function. I would like to take the gradient with respect to h of xi. Any suggestions? All right, okay, you take a minute and discuss it with your neighbor. I want everybody to figure out what that loss function is. So here's my loss function. I would like to take the gradient of L with respect to h of xi. All right, who can tell me? What is the loss function? Someone who hasn't said all that much? What's the gradient? Yep.
The sum of negative yi
e to the negative yi h of xi, but actually it's not a sum because all the other terms are 0. Because we only take a derivative with respect to h of xi. Yeah. So, good. So where are we in the boosting process, right? So we assume we've already taken some steps. Now we are right here. And now we want to know which direction to go next. So what we're doing is we're computing the gradient of the loss with respect to every single dimension. And that gives us some vector here, right? So that's basically what that is. In every single dimension, basically, this here is the gradient. Okay? So far, so good. And let's just call this is our Ri. That's how we call this, Ri, in the past. And so here's what I want to do. I just to make notation later on easier, I call this thing here Wi. It's called actually Wi hat. All right? Why not? And that's a weight. So this is basically, what is this? This is basically the loss. If you just look at this, is just the loss of this particular data point. Okay, how much does this particular data point I contribute to the loss function? That's what it is, right? And you sum over all of those. That's the loss. Okay? Raise your hand if you're still with me. All right, good, good, good. And we call this thing here, and let me do something else. We call Z the loss. I already wrote it down. This thing here, I just call this Z. Okay? This is the sum of all, it's basically just the sum of all the losses, right? That's the overall loss. And then I say Wi equals Wi hat over C. Now, who can tell me what's the sum of all the I, Wi? Give you a minute. Discuss it with your neighbor. Give you one hint. It's not Z.
So Wi in what?
Yeah. It's 1, exactly. It's 1. Why is it 1? That's right. So this is basically sum over all IW hat over Z. And what's the sum over all W I hat? That's this. And if I sum over those, that's exactly the definition of Z. So it's Z over Z. It's 1. Okay? And they're all non-negative. So really, in some sense, they're kind of weights. Right? That's why I call them W, actually. They're weights. Okay, good. So far, so good. So just remember what we're trying to do, right? We are somewhere here. We have our H so far. We're trying to find the direction in which to go down, right? To most increase our loss. How are we doing this? We're computing the gradient, right? Of the function L with respect to every single dimension, right? Sure, why not, right? And this is what we get, right? Okay, good. And now we want to find a weak learner that is best aligned with the gradient. Okay, we would like to find a weak learner that ideally kind of points exactly in that direction. So this is how we find h of xi. So our next h of xi equals arg min. And this is exactly from last lecture. So within our set of weak learners, we try to find the weak learner that minimizes the inner product, right, between this gradient and the output of the weak learner. So what we go is we go over I equals 1 to n, h of xi times the gradient. Well, the gradient is this thing here, right? So that's wi e to the minus yi h of xi. We have a minus. Okay, raise your hand if you understand what I'm doing here. That's not many people. Okay, yeah? Oh, sorry, that's a y. Yeah. Okay, good. Thank you. Good. Okay, good. Wait, I made a mistake. This was my yi. This was my yi. Okay. Okay, we can also do this. We can also do w hat of I. Yi. Okay, is it now correct? Okay, good. Okay, so one more time. Guys, pay attention. Right. So here's what we do. We are here. This is our h of x. This is where we currently are. This is our h. Now we try to find a direction. The gradient points in this direction. This here is my gradient, right? And this gradient, what does it look like? It's like, R1, R2, Rn, right? That's my vector. I want to get something where each r is exactly this. I want to find a function. The only thing is it points in the other direction because gradients point in the wrong direction. Now I want to find a function h that is aligned, that points down here, right? So what I want to do is, I want to find a function h that has minimum inner product with this here is my Ri. Right? So this is basically the inner product between the R vector and my H vector. Right? So I just go over all dimensions and I just compute H of xi times Ri and so on. And that's exactly the inner product between these two vectors. So if this is very, very large, then I'm basically pointing exactly in that direction. Raise your hand if that makes sense now. Okay. If it doesn't make sense, please read last lecture's notes again, because that's exactly what we derived last time, that you basically have to minimize this inner product. Okay, let's just go ahead from here. One thing we can now do is we can actually now divide by z, right? Because why not? It's a constant, right? And then this here becomes my wi here. Okay, so given the previous step, does that make sense, the next step? I just took this and just multiplied by 1 over z, and now I get, instead of a wi hat, I just get wi, because wi is wi hat over z. Raise your hand if that makes sense. Okay, good. We're almost there, guys. We're almost there. Let me rearrange some terms. wi, yi. What is this? H of xi times yi. Can anyone tell me what those, what values does that take on? Yeah? That's right. It's either positive, it's either +1, or it's -1. Okay? If this guy gets this point correct, it's +1. If this guy gets this point incorrect, it's -1. So this is in +1, -1. Okay, cool. Now, last step. Pay attention for one step. We're there. All right, here we go. We now divide it up. Actually, 2 more steps. I lied, but you know. All right, 2 more steps. So here's what we do. This is either +1 or -1. So what we do is we just divide up the sum. We sum over all the points where it's positive, and then we sum over all the points that's negative. Right? Why not? So we first sum over all the points that's positive, I such that yi equals, or h, let's do it this way, h of xi equals 1. And this is always 1, this is just wi. Plus, now we sum over all the points where it's negative. It's -1. So then this is just minus wi. Okay? Raise your hand if that statement made sense. Okay, awesome. Good. We're getting there. Okay. Now, can anyone tell me what this is? This is kind of tricky. I sum over all my data points. Actually, let's do this one. This is easier to interpret. Let's do this term here. I sum over all my data points where yi h of xi is -1, and I sum up their weights. So I'm summing over all the points that I got wrong, and I sum up their weights. What do I get? Do you want to say it? Yeah?
1 minus the weight versus you got right.
Yeah, this is basically the weighted error, right? It's basically if I give every data point a weight wi, and I sum over all the points that I get wrong, their weights, and that's basically the amount of weight that I got wrong. This is the weighted error. This here is the weighted accuracy. All right? So let's call that weighted error epsilon. Let's call this thing epsilon. All right? Why not? Then what is this? All right, this here is epsilon. And what is this? It's 1 minus epsilon. Exactly. Right? So what we get is the following. So we have here minus 1 minus epsilon minus epsilon, and that gives me epsilon, plus minus some constants that I don't care about. Okay? So, what does that mean? It's actually a really profound result. All right, let's just put it back in. So what we are minimizing is sum over all I equals 1 to n. H of xi not equal yi wi. Let me illustrate to you what that means. You basically have a data set. Oh wait, I can do this. This is really fancy. You have a data set of positive and negative points. And each one of these points has a weight associated with it. So let's say this here is 0.3, you know, but 0.05, 0.025 or something, you know, 0.025, etc. Every point has a weight associated with it. Or I can also draw them smaller and bigger. How about this? Right, this guy's a big weight, so it's big. Right? This guy's a small weight, it's tiny. Right? And what I'm trying to minimize is the weighted error. That's it. Right? So I want to find the h that minimizes my weighted error, right? Which is basically, here I'm going over all data points that I got wrong, and I sum the weight of all the points that I'm getting wrong. That's what I want to minimize. Okay? That's the idea. And the weights are defined in a very specific way, but it doesn't really matter, right? So this is my definition of the weights. Where is it? Somewhere here. Where are my weights? I guess it disappeared, but it used to be there. It was beautiful. All right, so what you need for Adaboost is an algorithm that takes in x's and y's and weights, and it tries to find you the lowest weighted error. Right, and if you can do this, then we can do boosting. Any questions? Yeah?
So for exponential error, and because we only have two classes, aren't our weights all going to be the same? Because it's all just e to the negative y, e to x.
Oh no, oh no, oh no. So see, initially, oh yeah, okay, good. Initially, right, so initially what he's saying is my h of xi is just 0 or something initially, right? Well then each one of these weights is 1, right? And that's great, that's what we want. Initially we get a data set, and everything is equal. And then what Adaboost does, and this is basically the idea. We have data point, everything is equal. Now we run the first classifier. Let's say you put it here. We say, oh, this is positive, or this is negative. These points here are all correct. These 3 points are wrong. This point is wrong. So what will Adaboost do? It will now increase the weight of this guy by a lot. Increase the weight of this guy and this guy. I just say like, look, these guys are much bigger now. Right? And now it runs another classifier and say, now run it again. Try to get this data set right. And now it won't misclassify these data points anymore, because these are now really, really heavily weighted. Right? And these have very small weight in comparison. So now you get a different classifier. Maybe it does this, right? It basically says, these are negative, these are positive, right? And now this guy is misclassified. So what it will now do, will give this guy a larger weight, and so on. Right? So every iteration, you re-weight your data points. And you give those data points that you're still getting wrong more weight. And those that you're getting right, lower weight. And not only this, we will get to this in a minute, the weight increases exponentially. Right? So if you get a point wrong repeatedly, at some point you will have all the weight on that one point. It's like, damn it, I'm going to get it right. Right? Until you get it right. And then it will back off again. Right? So it's, but using this, by doing this, it has a lot of power. Right? It can basically enforce that every single data point, no matter where it is, will eventually get the attention it needs to get it right. Right? That's basically what's going on. That's the intuition behind Adaboost. Any questions? Yeah? Minimizing the, yeah, that's the same thing, right? So minimizing the error is the same thing as maximizing the accuracy. Yeah, it's the same thing, right? Because one is 1 minus the other. So the accuracy is 1 minus the error. Yeah, absolutely. Yeah, question? Sorry, say that again, one more time. Yeah, no, but the nice thing about Adaboost is you can take classifiers that are very, very, they're very, very simple, right? And so they would get a lot of points wrong, but now the next time you take these points and weight them higher, right? So boosting SVMs doesn't make too much sense, actually, right? Because they're already, as you're saying, they're already doing that, right? But they're specific to there's various reasons why occasionally you want to use Adaboost, right? And in part because decision trees are just great algorithms, so you can just boost trees, but you can actually boost anything. Right? Like just in SVMs, you won't get much benefit anymore because they don't really have a bias problem, right? It's really, this is a bias issue, right? So here the classifiers are biased towards these lines. Yeah, last question.
Does it cost overfitting because you're looking at each and every point and changing the weight?
Yeah, so the amazing thing about Adaboost, and when I started my PhD, there was like when you went to a conference, this was with everybody, like you went for a beer afterwards with some people from the conference, everybody was talking about why does Adaboost not overfit? And nobody knew the answer. And it was this open question. Like everybody in machine learning was scratching their heads about it, right? It was reducing the error so quickly, and it was so powerful, yet it didn't overfit, right? And the curve just didn't look like it. Like, if you looked at, here the number of iterations, there's number of iterations, the training error went down like this, very, very quickly. And the testing error looked like this and didn't go down. And nobody knew why. Like every theory, like, we had no reason. Like nobody could make, rhyme or reason about it. And then actually it took a long time. And in fact, the computers just got faster. Right? So, but basically, at some point, people actually, what they did is they just kept boosting for a really, really long time. And then what they saw is that it slowly goes back up, slowly. And then actually, turns out if you plot this on a log scale, if you just say here, log iterations, that actually just looks just like any other curve. So basically, the amount it overfits actually does not, basically grows at a logarithmic scale. There's good reasons for this, why this is the case. So yes, they do overfit, but the beauty of Adaboost is that it overfits really slowly, which gives you a lot of flexibility to find the sweet spot when to stop. Right? And that's why it's so, so, so powerful. Right? It's really hard. If you have so much time in the world, it's slowly starting to overfit, but yet you still keep boosting for another week, right? Well, that's really your own fault at this point, right? So you really get, very good heads up in some sense, right? That's very different to decision trees. So the decision trees, they go down and bam, go back up, right? So they overfit like very, very quickly. Yeah, and actually, this is what, Rob Shapiro actually, so he invented boosting and then he went to Princeton, and for 15 years, he basically worked on nothing else and tried to really understand. Now he wrote a book about it. I think there's multiple chapters on that question. So it is counterintuitive, and that's why it was so surprising. Actually, I can explain you why though. Here's the intuition. The intuition is that these alphas get really, really tiny, right? Because you basically get closer and closer to the loss. So at the beginning you take gigantic steps, but because you do this line search, right? There's very little to be gained from each step. So you add very, very small alphas. So actually you're doing a lot less, right? And as you keep going, your alphas get smaller and smaller. So the more you're adding, the less you're actually changing. Does that make sense? So you take at the beginning you take really large steps, and then you take really, really small steps. So that's kind of this built-in system against overfitting. All right. I have another derivation for you guys, but I feel like people are kind of done with derivations. Who wants to see demo first and then derivation? Who's for demo first? Raise your hand. Who's for demo second? Some people are hardcore. All right, good. You know what? I think it's a tie, so I can choose. All right, good. So here is again, one thing I want to show you is, okay, first the good old demo where I play some dots. And so let's make some challenging data set. This is decision trees. So I'm boosting some decision trees. These are very little decision trees. So any suggestions?
Interleaved spirals.
Interleaved spirals. Okay, you guys are nasty. All right. All right, okay, good. I think this is actually against, some conventions, treatment of algorithms, but okay. All right, let's do this. Just make them yin and yang, that's more positive. All right. Okay, good. Oh yeah, okay. Woo. Okay, shoot. So what you're seeing here, this is the decision boundary, and it adds little classifiers, right? And it's trying to basically get the points right, and it keeps reweighting them. And So this one actually got all the points right already. Right? So the error is 0. The error on the right-hand side is the black line. The red one is the loss. So the loss keeps going down still. So it still actually adds classifiers to the ensemble, right? And it basically refines the decision boundary, right? So it keeps adding trees, And what you see here, the red thing is where it's very, very sure it's positive. Blue thing is very sure it's negative. And so, here's kind of the regions where it's not entirely sure, right? But it gets it right? It really cuts around nicely around this spiral, right? I mean, this is really a really good decision boundary in this case, right? It makes a lot of sense, right? And the amazing thing is this is just built out of these very simple trees, right? So just by adding them repeatedly, and then you see, your question was like, is it going to overfit, right? And you see now actually, like the decision boundary doesn't go crazy, right? It doesn't do silly things, right? Like decision trees we saw, they kind of did really silly things to cut out one point. Here we keep boosting for 200 iterations now, right? And really cut it out very, very nicely. And this is probably, a reasonable decision boundary. Let me maybe do one more example, now that you know what to look at. Any other data set? Centric circles. That's easy. That's too easy, actually. Because decision trees can do that by themselves, right? It's, it's like the boosting algorithm will laugh. Add noise? Oh, okay. Oh, you're nasty. Okay, you got it. So here's the problem with Adaboost. Adaboost is actually anal retentive, right? So when there's this little point that's mislabeled, it just can't look past it, right? It's going to give it all the way. It's like a little piece of dirt, right, at your grandma's house. He's like, now I got to clean it away. That's what you get. All right, here, like very prominently here. Actually, that's probably too. It's put right in the center. Oh no, that's so nasty.
Yeah, do it.
Oh, I feel bad. All right, okay. All right, okay. Here we go. But I had to. I was forced to do it. Okay, here we go. So it's cutting out, right? But it still has this one point. It's fighting. It's fighting around that piece of dirt. It keeps scrubbing. Oh no, got it right. It got it. It actually got it, right? It cut around it. But it will not stop until it gets every single point right? It just at some point it just gives this point all the weight in the world, and then, it always gets it right. Okay, yeah. Yeah, I actually have another demo, but it's not very good. This is actually, I don't like this demo, but I show it to you anyway. Wait, what is this? And this is actually, so now what you can see is actually the weights. So let me do the spiral again because it's interesting. It just gets very messy. So I tried to make this look cool by making the points large, but it didn't work. So I apologize. This is below my demo standard. Like, I only show it because you asked for it. All right, here we go. So let's do this. And what you see is, you see the weights. You see some points are really, really large, right? Like, and a lot of points are basically disappearing, right? You see these points where it's really short, they're disappearing. They're below 1 pixel now, right? It doesn't care about them anymore, right? But it's still fighting around these points in the decision, where the decision boundary is, right? They're just, it just obsesses about them, right? And it keeps getting back and forth between them. So basically adds one that gets a circle right, and then it gets one that gets a cross right, and it gets them, alternates between them, right? And so some points, you see these on the right, this is quite nice. These crosses on the right, they disappear, then it gets them right, and then doesn't care about them anymore. You see, now it got them wrong again, right? So then it's like, oh, wait a second, right? It's a little like whack-a-mole, right? Whatever that is. All right. Okay, any more questions? Yeah? When does it stop? Adaboost never stops. Adaboost will never stop because the loss is always non-zero, right? Because e to the something, but it can never reach 0. Only in the limit will it reach 0. So Adaboost will, when we are all dead, right? Adaboost will still be boosting. Yeah. Any more questions? Okay, I can show you one more demo. This is bias variance boost. So here's the good old data set of, actually let me show the data set this time. Okay, good. So this here is the data set one more time. So I have positive and negative points, and I try to separate them And I believe I have very simple decision trees that just have one split, I believe. So it's a little bit artificially easy data set, but it's very noisy, right? So this is quite bad for Adaboost, right? So this is what it can't do all that well. And what I'm showing you now is the decision bound, the bias variance curve. And so this is actually not a great example, but what you see is initially, right, the bias is really high, right? And the first iteration of boosting, like after 3 iterations of boosting, the bias got, halved, right? It's now, from 0.02 to 0.01, right? The second thing that's very interesting is, as that goes down, the variance, this is the black line is the variance does not increase, right? This is actually quite noticeable, right? Similar to bagging. Bagging reduced the variance, but did not actually increase the bias. Adaboost is pretty good about not increasing the variance, right? Eventually it will go up, but this takes a long, long, long time, right? So here actually, basically the error goes down very quickly, and so the bias goes down very quickly. Here at this point, it doesn't, it goes down very, very slowly because this is a very noisy data set. So what happens is it just obsesses over the noise, right? So Adaboost is not great when it's too noisy. That's the weakness of Adaboost. But I mostly want to show you this for this beginning here, where you see this massive drop in error, right? There's really a huge drop, right? With just a few iterations of boosting. This is, by the way, the test error. This is not the training error. The training error has long been 0 at this point, right? Any questions? Yeah?
Just a random question. For all of these graphs, variance has always been above bias. Is that generally true for
yeah, with this data set, it was hard to find a data set that's an algorithm that's so biased. It's not generally true. Yeah. It's just because I have this simple 2D data set. And so in some sense, actually, you can actually have a line that's actually the optimal classifier. Right? Okay, good. Oh, I see, I can do one more. This is actually the spiral. This is a Kant spiral. Wait, spiral. Okay, I forgot what that demo is actually. Oh yeah, okay, so this here is actually this is a more complicated spiral. And what you see here is basically the exponential loss goes down very, very nicely. The training error is already 0, right? And so here's basically the spiral. In some sense, it cuts out the spiral. This is a very sparsely sampled spiral, so decision boundary doesn't look as cute as it could be. But one thing is nice, the testing error does not really shoot up, right? And this is really, I think, something you should note, right? So as you start boosting, you get this initial drop, this massive drop of test error, and then it doesn't really go up very much, right? So boosting is really very forgiving for that, right? So you can boost for quite some time and then find the lowest validation error. It's not a problem. The other thing that I really want to emphasize, and we haven't shown this yet, it's the loss is actually an upper bound of the training error. So once the loss is lower than 1 over n, you know you must have 0 training error, right? Because it's an upper bound, the loss is always larger than the training error. And so the loss will go down every single iteration. So that is why boosting will always give you 0 training error, right? Because you're driving down the loss, and the loss is an upper bound. All right, any more questions? All right. So maybe we spent the last few minutes looking at the proof of how to find the step size alpha. And the most amazing thing about this is, I'm just going to show you the problem setting, and then I want you and your neighbor to kind of look at it independently. Not independently, by yourself. And that's the following. Imagine you now found this classifier H, right? We now know how to find this classifier H. We just get our weights, we give the weak learner the weights of the data, and it returns us a weak learner, right? So now what we like to find, so now we have this H, we we would like to do the following. This is our new classifier. H is done. This we have from the previous round. Alpha we don't know. So we would like to know the alpha that minimizes, this is the line search, that minimizes this expression. So what that means in the space here, we have our point H, we have our loss function. It gave us a gradient, it gave us an H, which let's say points in this direction because they're pretty bad. And now we would like to find how far do we have to go to minimize this function, right? And so it turns out this is actually a closed form solution. So if we do this, it turns out alpha is just 1/2 log of 1 minus epsilon over epsilon. That's it. Where epsilon is the weighted error. This is the accuracy over the error. That's basically what it is, right? The weighted accuracy divided by the weighted error. You take the natural log and times 1/2. That turns out to be always exactly the right step size. The proof is here under finding the step size. So why don't you and your neighbor just, start reading through this and just make sure you understand every single step. This, by the way, why Adaboost is such magic, right? Because this here is trivial. This is 1 line of Julia, right? 2 lines of Python, right? So this is really, really simple to implement. Adaboost, to implement Adaboost is literally 5, maybe 7 lines of code. And by the way, that's exactly what you will have to do in the next project. So this is coming out today, maybe tomorrow morning. You have to build in decision trees and Adaboost and bagging. No, everything just works out so beautifully because of the exponential loss.
Oh, okay. So other losses don't have closed form.
That's right.
Okay.
They also have other names. There's logit boost, there's logistic loss, right? So for most people have now analyzed all of these loss functions. It just turned out that Adaboost, it was the first one, actually has the most beautiful properties.
But we can still optimize the alpha with other losses, right?
Sorry?
We can still optimize the alpha with other losses.
Often it does not have a closed form solution. Or you can't. We could do a line search. Yeah, you could just try out 30 alphas and pick the lowest one.
But it's not closed.
It's not closed form. Yeah. All right, good. Time is up. Why don't we continue this next time, please? Until next lecture, please read through this little proof, and you come in with a head start.